So our last chapter is chemical and phase equilibrium. We're only going to cover a little bit of this because we're out of time for the semester. But some of these topics can help you with understanding a little bit more about chemical reactions. So first, the equilibrium criterion. We said back in chapter 11 that a system would be at thermodynamic equilibrium if the Gibbs energy was at a minimum, Gibbs energy being H minus Ts. And it was just a combination of other energy and entropy terms, somewhat like H was U plus PV. And the chemical potential was the partial molar Gibbs energy of the species, or the change in the Gibbs energy with the change in the number of moles of species I. If I wanted to write an equation for this minimum Gibbs energy, what I would find is that the chemical potential times the change in number of moles of each of these would have to equal 0. Now this is a great definition of equilibrium. It would allow me to solve a lot of problems if I just understood better what this chemical potential was. So we're going to kind of come at it a different way. We're not going to really calculate that chemical potential. And we're only going to be able to solve some problems using this technique, but it would be a starter to get you into other problems. So first, let's talk about what reaction equilibrium is. Technically, every reaction is an equilibrium reaction. A lot of times you put some materials together and you wait a while, and at the end you have no reactants left, you have just product, and we would say that the reaction goes to completion. Other times I put two molecules together and I wait a long time and they don't ever appear to react, and so I would say that the stuff just simply did not react. But what we really want to talk about is those cases where I have measurable quantities of both reactants and products. So here is a chemical reaction. It's an equilibrium, meaning it can go forward or backward, and it's been balanced with stoichiometric coefficients nu A, nu B, nu C, and nu D. If I wanted to talk about how many moles of each species were added or subtracted as this reaction progresses, I would be looking at the change in number of moles. And A is going to decrease, B will decrease because they are on the reactant side, C and D would increase as the reaction progressed towards products. But the amount that would change is related to these stoichiometric coefficients. And so if I define something called d epsilon, epsilon being the extent of reaction, that would be something that would have a stoichiometric coefficient of 1, whatever that would be. Okay? And for a stoichiometric coefficient of 1, it would be equal to the change in moles of D divided by the stoichiometric coefficient of D, or the negative change in moles of A divided by the stoichiometric coefficient of A. So I could solve for the change in number of moles of each one of these based on the stoichiometric coefficient times d epsilon. And the stoichiometric coefficient is negative if it's this side, because as the reaction progresses it disappears, and it's positive on this side because as the reaction progresses it appears. And at equilibrium I would expect that the chemical potentials would all be 0, the sums of all of these. Now, if I were to then look at this in terms of number of moles, I can then use this to calculate the number of moles. So if I initially have this much and the reaction has gone on for a period of time so that a portion has reacted, then I would have this as the amount of change. And that would be the moles at the end of the reaction. And I could do that for each species. And I could therefore calculate the mole fraction species by species, where nu is the sum of stoichiometric coefficients taking positive for product, negative for reactants. So let's look at an example and see if we can make this make a little bit of sense. So here I have 6 NO2 plus 8 NH3 makes 7 N2 plus 12 H2O. Okay, so whether or not you understand the reaction, just accept that it is a correctly balanced equation. Okay, so I'm going to have 6 molecules of NO2 and 8 molecules of NH3 combining to form 7 N2s and 12 H2Os. The change in number of moles of my total mixture is 7 plus 12 minus 8 minus 6. So a change of 5 additional moles of product gas would be formed. So if I want to look at what's going to happen to the mole fractions at equilibrium, I simply need to take, well, if I start with a feed of 10 moles of NO2, okay, and 5 moles of NH3, then at the end I will have 10 moles of NO2 less the amount that reacted, 6 times epsilon. NH3, I started with 5 moles, 8 epsilon reacted, so 5 minus 8 epsilon. My nitrogen, I started with none, and 7 were formed, 7 epsilon. And my water, I started with none, 12 were formed, 12 epsilon. Now then, how much total did I have? Well, I could add up all of these, or I could simply say, well, I started with 15 moles total. And I added 5 epsilon total, so 15 plus 5 epsilon. This allows me to get a mole fraction as the reaction progresses, 1 molecule, 1 mole at a time. So we'll pause now and we will come back in our next video and look at how we calculate equilibrium compositions.